MDM4U 8.5 repeated sampling and hypothesis testing. Part A is going to discuss repeated sampling. Population, all members that belong to a group being studied. And a sample is a group of items or people selected from a population. So this is an image to illustrate this, that a sample is just a selection from that entire group, the population. And in this case, it looks like we're talking about a survey, but this can be involving a random variable x, and we can be talking about data values as well. So, to clarify the following, a parameter is a number that describes data from a population. So if every single member of the population is selected, then we could say that it has a mean of mu and a standard deviation of sigma. So these symbols are used to discuss the mean and standard deviation of the population, and a statistic is a number that describes data from a sample, so your selection from that group. And the symbols that are used to denote this for a sample, the mean is x bar, and the standard deviation is s. So these are statistics, whereas our statistics help to approximate a parameter about the population. So, repeated samples. In short, that means that it is a sample with multiple values taken. When repeated samples of the same size are drawn from a normal population, the sample means will be normally distributed with a mean equal to the population mean mu. So that means that we expect that the sample mean, or the distribution of sample means, will be clustered around the true population mean. Sometimes it'll be above, sometimes it'll be below, but the average of all of the sample means will be close to the population mean, mu. The distribution of sample means will have a standard deviation of x bar is equal to the standard deviation of the population divided by the square root of n, where n is the sample size. So let's discuss why this is the case. As n increases, this total value, the standard deviation of the sample means, becomes smaller. So with just one observation being taken multiple times, this is the same as the population's distribution if our sample size was 1. But whenever we start taking samples that are larger, the distribution of sample means will be clustered closer around the population mean, closer around the center. Because think about this, if we're taking a sample average of size 10 versus a sample average of size 100, it's probably a better estimate of the true population with the group that's taken at size 100. So we need to adjust the sampling distribution of sample means based on the number of observations that we're taking in each sample. Okay, so notice that if n is equal to 1, the samples are a single data point, and the standard deviation of x bar is equal to the standard deviation of the population. As n increases, however, the standard deviation of x bar, or the sample means, decreases. So the distribution of sample means becomes more tightly grouped around the true mean. Usually a sample size of at least 30 is sufficient to give a reasonable, accurate estimate of mu. So that number 30 is just taken as a trivial number, but it's a rule of thumb. 30 or more is an accurate or reasonable estimate of mu. And this table summarizes our results. So that being said, the sample mean x bar, the standard deviation of the sample means is the standard deviation of the population divided by the square root of n. So we're going to look at an example from the textbook. Example, tire wear. The tires on a rental car fleets have lifetimes that are normally distributed with a mean life of 64,000 kilometers and a standard deviation of 4,800 kilometers. Every week, a mechanic checks the tires on 10 randomly selected cars. What are the mean and standard deviation of the samples? How likely is the mechanic to find a sample mean of 62,500 kilometers or less? So let's start off with part A. What are the mean and standard deviation of these samples? So the mean of the sample means is equal to the population mean. It's a good approximation of the population parameter. the distribution of, sorry, the mean of the sample means. It'll be centered around the mean. So we'll take that to be 64,000. And our sample size is 40 because if we have 10 cars that we are observing every week, there's 4 tires on each car, so there's 40 tires in total. And the standard deviation of sample means is given by this formula. The standard deviation of sample means is the population standard deviation, 4,800, divided by square root of 40. So approximately this value. So what we're going to do is, for part B, how likely is the mechanic to find a sample mean of 62,500 kilometers or less? We are going to use our sampling distribution results in order to calculate this probability. So the probability that x is less than 62,500 is being approximated by the probability that a z-score is less than the deviation with regards to the sampling distribution. So we've calculated the sampling distribution. So the mean of the samples is 64,000, similar to what the population would be, but we've adjusted the standard deviation of the sampling distribution, or the sample means, would be equal to the value that we calculated. This has a z-score of negative 1.98, and you can use the z-score table in order to determine if that probability is approximately 2%. Okay, so what we're going to add to this is something that should give us a better understanding of what exactly repeated sampling is. So, an IQ test is a measure of someone's intelligence based on mu being 100, the average intelligence being 100, and it has a standard deviation of 15, and this is all based on someone's age and their population for intelligence quotient on that test. So remember, repeated sampling means that if we're taking a sample, and let's just say we're taking 10 people at a time, that's why there's 10 trials. The sample mean is adding these numbers and dividing by the total to get the sample mean for sample 1. Now what I've done is used a random number generator in order to come up with the sampling distribution, where I have a random number generated, the mean is 100 and the standard deviation is 15. So every time that I click on this, this actually generates a simulation. And I have used 1,000 different samples to come up with our sampling distribution. So I will give you a small proof. It keeps going and going. Now that being said, let's take a look and reinforce some of those concepts that we've learned. The mean of the sampling distribution. So that would mean these values here at the bottom, which is the samples mean for each of these different columns, for each sample. These are the values that we're talking about when it comes to the mean of the sample means. All of these. Now, the standard deviation of the sample means is using that same data. And this is that adjustment that we calculate for the standard deviation of the sample means, or the sampling distribution, is approximately 4.7. Now, we can just reinforce that by running a quick test. We're doing another 1,000 samples, and it is pretty close to 4.7 every single time. So that's just a demonstration that this is an accurate estimate. And notice this, I've just included max and min to see what is reasonable in order to be able to draw a histogram to represent this data. So, that being said, what I can do is I selected bins, and I saw that it was typically between 75 and 125 for the max and min value for our sample means. So what I did was select those bins, and I used the data analysis tool. So data analysis, histogram. I'm selecting the input range, all of those sample means, and the bin range is all of the ones that I've selected all the way up to 125. And then I'm outputting them here, pressing OK. Now this is going to override the previous result, but you can see that it's creating approximately a normal distribution. It is symmetrical, it is unimodal, and that's why it's reasonable to approximate some of these probabilities using the standard normal curve.